a 3-session, 2 hours each on this Saturday, that is 14th, and on 21st and on 23rd, where we will be covering the basics of deep learning, machine learning, deep learning, and also the tools with which you will be able to do the machine learning in practice. So where we will have a hands-on experience on the deep learning workflow. So you'll be working with TensorFlow and Keras. So before going ahead, so let me let me welcome all the participants from across India. So from various places in India, the faculty members who have joined, and also a few from abroad from the Gulf region. So let me welcome them as well. And also let me welcome the faculty members from Saintgits and some of the interested students from Saintgits. So because there are some external participants, let me mention a word about Saintgits group of institutions, which is located at Kottayam in Kerala, the southern part of India. We have Saintgits College of Engineering, which is an autonomous engineering institution. Along with Saintgits College of Engineering, we also have Saintgits Institute of Management, which is also autonomous. We have Saintgits Institute of Computer Applications, which is also an autonomous institution, where we have the freedom to have our own curriculum and include the latest trends in our curriculum and syllabus. So this Saintgits College of Applied Sciences is another sister institution, which is also part of Saintgits group. So Saintgits Institute of Artificial Intelligence and Machine Learning is a new initiative of Saintgits. So we will be offering various courses, training programs in the due course through Saintgits Institute of Artificial Intelligence and Machine Learning. In this particular sessions, the topics that we will cover, so we'll be giving you an overview of artificial intelligence and machine learning. And in order to understand machine learning, you should clearly understand the difference between the traditional programming. And so I'll be touching upon the difference between the traditional programming and machine learning. And then we'll move on to a basic hands-on session with TensorFlow and Keras, where you will get some basic introduction as to how you will be able to use the TensorFlow commands to model and to compile, etc. And then moving on from a simple task, we'll move ahead with a computer vision task where we'll try to classify an image. So that is an activity recognition. We'll try how we'll be able to recognize an activity, and then I'll try to tell you why the traditional programming has limitations and the need for machine learning. And after this hands-on session with TensorFlow and Keras on image classification, so we'll just mention the various tools and applications using various tools that can be used for machine learning and deep learning, and the applications using deep learning. And finally, we'll also touch upon some of the ethical issues. In order to save the bandwidth, I have switched off my camera as well. So I hope the slides are visible to all. And again, as I said earlier, so please mute your microphones. If you have any questions, you can post it in the chat box. So we'll take up the questions and discuss them towards the end. Okay, so let's start with the video. So this particular video, this is from NVIDIA. So this is a video which they played for their GPU technology conference. And so we'll get an idea about the power of AI.
the expanses of space to keep our planet safe. And all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel. And a sea of people to find a lost child. I am a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. And make us whole again. I am a visionary, enabling taxis that don't need steering wheels. That don't need roads. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Yeah, so I hope you got an exposure to the power of AI. AI is a visionary, a composer, a protector, a guardian, and AI is changing the world we live, the changing the way we work, the changing the way we experience this particular world. And everywhere we see the impact of AI, machine learning, and deep learning. So we keep using many words, artificial intelligence, machine learning, deep learning, and there are so many jargons associated with these technology. So let me, to start with, let me just tell you what is artificial intelligence, what is machine learning and deep learning, what is the connection. Some of you who have already got some exposure might have clarity about this, but I know that there are some new people who are interested, some enthusiasts. So artificial intelligence, this particular word, as you can see, this is the this particular lighter green area. So there you can see that this artificial intelligence, this was there from 1950s. So from 1950s, and during that time itself, we used to hear about some artificial intelligence programming languages like Lisp and Prolog. And it was during 1950s where 1959 and early 1960s that IBM came out with Deep Blue, which was able to, so they created a chess game which using this artificial intelligence technologies, and they were able to defeat some of the chess champions. So from early 1950s itself, we used to hear about artificial intelligence, but it did not take off that much till 1980s. From 1980s, so the machine learning and some of the algorithms associated with machine learning became a little more popular. And we can say that machine learning is a subset of artificial intelligence. So where you are trying to use statistical methods to model data and infer meaning from this particular data. There were many techniques, and from 1980s, machine learning and some of the works related to machine learning started coming out. But it was in early 2010, 2012, a breakthrough took place. It was in 2012 that Alex Krishoff, he was a PhD student of Jeffrey Hinton, the famous artificial intelligence and neural network expert. So he was a PhD student, and while doing his PhD, he took part in the ImageNet challenge. And in 2012, he developed a neural network. So where he used many deep layers of convolutional neural network, and he worked using a graphic processing unit, using a GPU. And so he was able to achieve breakthrough results in 2012. And his result was around 10% higher than the runner-up's result. So earlier, there was only marginal increase in this ImageNet challenge each year. But in 2012, this was a breakthrough because around 10% of increase. And then they realized the power of deep learning, where they realized that if you are earlier when they were using these machine learning algorithms, they were not using so many layers of neural networks. But from 2012, so many people started using these layers of deep neural network, and they also started using the graphic processing unit, and deep learning became powerful, and so many products started coming out using these deep learning. So basically, you should understand that machine learning is a subset of artificial intelligence, and deep learning is a subset of machine learning. So where you're using deep layers of neural network powered by GPU. So we can define, or we can say that AI is a broad field of study focused on using computers to do things that require human level intelligence. Machine learning is an approach to AI that uses statistical techniques to construct a model from observed data. And deep learning, or DL, is a machine learning technique that automates the creation of feature extractors using large amounts of data to train complex neural networks. So you will understand, so earlier when they were using machine learning techniques, so in order to understand if it was an image, in order to predict, or in order to understand this particular image, so there were some algorithms, like you had to identify the edge, you had to identify some of the corners, you had to identify some of the features of some of these images manually. But when deep learning came into place, so you could just give the image, and the deep neural networks, they were able to learn from the image and understand the various components inside the image. So that is why you say that you can bypass the human feature extraction in deep learning. Okay, so you will understand this better when you proceed further. So deep learning is very much in production these days. So you would have come across Apple's virtual assistant, Siri. So you can say, hey Siri, you can use a wake word, hey Siri, and you can wake up Siri, and you can ask Siri something. Or you would have heard of Alexa from Amazon. That's also a virtual assistant where you can also tell something to Alexa, and Alexa will search something for you, order something for you. So these are, you're trying to recognize the speech. These are all the results of deep learning in production. So some of you watch movies over Netflix, and you watch a movie, and then later on you find that a movie that you like is automatically recommended. So that's a recommender system. Or you search your Facebook, or you buy something on Amazon. So you see that after a few purchases, Amazon is able to recognize what are your likes and dislikes. Facebook is able to recognize what are your likes and dislikes, and they are able to recommend what you would like to see, what you would like to buy. These are the results of deep learning in production. I know that many of you have heard of autonomous driving, and you know about the driverless cars. And see, right now there are cars which are being produced, which are on the road, like Tesla cars, so which have a hybrid. So you can, maybe you're driving, and then after some time you can switch it on to, you can shift to the autopilot mode, and it can drive on its own. You don't have to, you can take your hands off from the steering wheel, and it will identify, it can identify the lane, and it can go and proceed. You can see the cars on the right, or the vehicles on the right, on the left, in the front, measure the distance. It can stop on its own. Yeah, there are challenges for deploying full-fledged autonomous cars on the vehicles on the roads right now, but there is a tremendous progress that is taking place. There are companies like, many companies like Amazon, who are trying to use drones, for autonomous drones, for delivering their goods. So these are all things that are right now taking place in this world, and which is the result of machine learning and deep learning in production. Yeah, so the technology behind this autonomous vehicles and all are based on real-time object recognition. You have to recognize the objects in front of you, on the right, left, everywhere. And so real-time object recognition has been made possible because of deep learning. Robotics, so robotic surgery is taking place. Robots can be used. I know that you know about Sophia. So I think it was a couple of years back for an IIT's technical event. The inaugural speech was delivered by Sophia. Sophia came, and Sophia is an autonomous robot. Yeah, so who can interact, who can talk with you. Real-time language translation, natural language processing, NLP, and real-time language translation, and how good it will be. You hear a speaker and you don't know that particular language. Somebody speaking in maybe Spanish or Japanese or Chinese, and then you are able to, at that time itself, real time, you are able to understand it in English. It is translated to you in English, and you're able to listen in English. So how good that will be. There are a lot of research and works going on in these directions as well. So machine learning and deep learning is an exciting area where a lot of things are happening, and let us explore these things together. So this is an important slide, an important picture, which has brought in a drastic change in the way the artificial intelligence and machine learning took off to deep learning in production. So this deep neural net, the combination of deep neural networks, GPUs, and big data. So the combination of these three has made the current deep learning a reality. Okay, the current products a reality. I just mentioned about the deep learning. Right now, there are so many algorithms, so many libraries, so many functions, so many companies are working on it, which are already available. Now we'll be looking at TensorFlow and Keras. There are Python itself, they have their own scikit-learn library, and there are so many such libraries which have made deep learning very easy, and you don't have to bother about so much of the mathematics behind it. And so, by the way, in this introductory course, I'll not also be touching upon the mathematics. Many times when you try to learn machine learning or deep learning, so the novices, those who would like to learn for the first time, they are sometimes bogged down by the mathematics. There are a lot of mathematics behind all this happening. So what is happening in a neural network, and how it is moving forward, how it is coming back, and what is happening. There are a lot of mathematics behind it. Yeah, it is needed to study this mathematics, and maybe in the subsequent sessions, some of these mathematics will be touched upon. But in this particular session, I want to give you a hands-on feel, just like you use a mobile phone. So you can use a mobile phone, you can dial a person, you can use the mobile applications on this mobile phone, which without knowing much about the intricacies of how to develop a mobile application, or how, what is inside, what are the components inside the mobile phone. Without that, you can use the mobile phone. So I want to create an interest in you to start using machine learning and deep learning. And that will be the approach I'll be following in this particular session. So as I said, deep neural networks. So this now we have an access to the deep neural networks through various models. We also have access to GPU, or graphic processing units. So NVIDIA, they are the pioneers. They brought out these GPUs initially. Those who are addicts to computer games, or those who are interested in computer games, you know about GPU. Initially, GPUs were developed for a lot of graphics and animations, and you wanted to play the games without any lag, and then you needed high computing power, and that is why they initially developed a GPU. But then later on, you understood that for these neural networks to function for training, and I'll tell you what is training. For training this neural network, you need high computing power, and with a CPU, it is not really practically possible. And GPUs are sometimes 10 times or more powerful than the CPU. And you found that you are able to get the required computing power through GPU. So along with DNN, you have GPU as well. And now for training a deep neural network, what is very much important, I'll tell you what is this training, and what is the difference between the traditional programming. But just understand that in order for the deep neural network to understand something, like human beings try to learn something. So we try to learn by seeing a lot of data. So you see, that, you teach a child what is an apple by showing a lot of pictures of an apple. And the child sees a red apple and a green apple and different types of apple. And then the child, when the child is exposed to an apple which the child has not yet seen, the child is able to say that this is an apple. So we all have learned like that by seeing data, by handling data. So this is the basic idea. For the neural network, deep neural networks to learn, it needs a lot of data for the training. And now, because of the internet, because of the mobile phones, because of the millions and billions of data being generated every day through mobile phones, through social platforms, through the internet. So the training the deep neural network has also become easy. So deep neural network, GPU, and big data, this combination has helped in deep learning taking off. And that is why we call it a big bang in machine learning, deep learning. Okay, so before proceeding further, let's watch a documentary. This is a 2-hour session. So during this 2-hour session, I want you to be engaged. So I'll be using lectures, I'll be talking to you. I'll also be showing you some of these videos. I've already showed you a brief small video. So this documentary, this is also a video. So where a person is visiting various happening places across the globe, in California, in Beijing, and a few other places, and looking at visiting some of the best research labs in the world, and seeing what is happening in AI, what is happening in deep learning, and also to understand what is deep learning. And I was mentioning about this training, and so you will get an idea about what is this training and all through this documentary. So let's watch this documentary before taking our discussions further. So after this documentary, so we'll also be working on some notebooks, so lectures, some videos, then you will be working on some notebook And that's how we'll be proceeding. Okay, over to this documentary.
Artificial intelligence is making rapid strides. There's talk of a new evolution that could fundamentally change life on our planet. Artificial intelligence has the potential to revolutionize every aspect of daily life: work, mobility, medicine, the economy, and communication. But will AI really make medicine better and doctors superfluous? When will self-driving cars hit our roads? Will intelligent robots usurp our jobs? And are we heading for a dystopia with no privacy and total surveillance? What exactly is artificial intelligence, and how much can it really do? What will change, and what will remain pure fantasy? To answer these questions, we embarked on an exciting journey to meet the scientists working on our future in the US, Britain, Germany, and China. First stop, Silicon Valley in California. Apple, Google, and Facebook all have their headquarters here. It's the epicenter of the digital revolution. The tech industry has changed the face of the San Francisco Bay Area. New startup companies launch every day. Rents have exploded, and artificial intelligence is the buzzword. A new type of supermarket recently opened its doors here. Amazon Go. All you need here is an app.
Since you have an Amazon account already, please
hold your mobile phone to the scanner and you're in. As Leonardo shows me Amazon's new menus and explains that the language assistant Alexa can help with the preparation at home, I'm under constant surveillance. Which shelf do I stop at? Which products am I interested in? On the ceiling, sensors and cameras. Intelligent image recognition captures my every move. What do I take off the shelf? What do I put back? And what do I take with me? This branch is still in its test phase, but Amazon plans to open 50 such grocery stores this year alone. The end of the sales assistant. Just walk out. No more standing in line. No cashiers. I feel a bit like a shoplifter as I leave. Comfort at the cost of privacy. My receipt. One block away, a robot cafe. Another test lab for the future. Order by app and touchscreen. The increasingly ubiquitous tools of trade. My first ever cup of coffee served by a robot. This is the taste of the future. AI will change our shopping experience, but what will happen to employees? Stanford University is at the forefront of global AI research with an annual budget of $6.5 billion. I want to know, how will artificial intelligence change medicine? Researchers here have developed an artificial intelligence algorithm that can screen X-rays for certain diseases. Computer scientist Pranav Rajpurkar shows me how easy it is to use. Take a picture of an X-ray with your mobile phone, upload the image, and a few seconds later, you get the diagnosis.
It's a mass, and it's saying this thing over here is a possibly cancerous lesion. And I can see that right over here.
Okay, so it gives you, if I may have a look at it, now probabilities for pneumonia, a nodule, edema, effusion, and that goes bang.
Yeah.
Now, how does this work? I mean, how did you get to the point?
We started with a large data set of chest x-rays, which were released by the NIH, and these contained x-rays and then also labels of different pathologies and whether they existed in those x-rays. So it might say, okay, here's an image, and on this image I have pathology 1, 2, and 3. And we had 100,000 of these images. So we trained a model that can take as an input an X-ray and then output the probability of several different pathologies on this X-ray.
Artificial intelligence is modeled on the human brain, a gigantic network of almost 100 billion interconnected neurons. Put in very simple terms, this is how a brain cell works. Incoming impulses are passed in a domino effect from one neuron to the next. The resulting circuit connects the neurons, and it is this circuit that artificial intelligence tries to simulate as a digital neural network. Like our brains, the network can learn how to identify tuberculosis, for instance. First, the network needs to be trained or taught. X-rays of tuberculosis patients are fed to the system. Initially, it struggles to correctly identify the condition. But every time an X-ray is fed in, the network's structure is adapted and its diagnostic ability improves. It takes thousands and thousands of clinical data sets to train the machine. Only after the network is optimized in this way can it correctly identify an unknown X-ray. But how accurate is artificial intelligence compared to a doctor's expertise?
We have actually done this test twice at this point, once with a set of studies from the NIH data set that we had a group of radiologists label, and then we compared the accuracy of the model to the radiologists, and we found that they were very similar in terms of accuracy on most pathologies. On one of them, the model was outperforming the radiologists, and on 3 of them, the radiologists were outperforming the model. And then we repeated the experiment, this time using a data set from Stanford, which we recently released, which is 200,000 chest x-rays. And then we had a similar setup where we had 3 subspecialty radiologists. These are very uncommon, very trained radiologists to decide what the ground truth for a particular set of images was. And then we compared general radiologists to the algorithm at the task and found that they had similar levels of performance. So these are all Stanford radiologists, so they're trained.
They should be good.
Yeah.
Reading X-rays accurately is a complicated process, but artificial intelligence is making fast progress. When it comes to identifying or recognizing simple images, computers have surpassed human accuracy.
So I'm sure this video has given you a very clear picture of the current state of artificial intelligence, deep learning in production. So you just saw how an X-ray can be just, a photo of an X-ray can be taken by a mobile phone, and it can immediately identify, classify that particular X-ray. Detect what is the sickness? Is it a tuberculosis? Is it what is the problem? So how did this happen? How did this training take place? How did the machine learn? Like a radiologist diagnose, how did this machine learn? So we saw that this is it was happening through a neural network. So here, this is a simple illustration of a neural network, which is something trying to simulate the brain. So where you have an input layer, you have a hidden layer, layers in between, and then an output layer. So when you're talking about deep neural networks, you will have so many hidden layers, so many layers, so many layers. And then for this X-ray, what you were trying to do is that you were feeding in the X-rays and you were feeding in the expected output to this neural network. So this expected output, that you call it as the label. You are giving the image and the label. So you are giving the image and the label. And then through this neural network, so from the output, you are supposed to get an expected output. Okay, so you are supposed to get tuberculosis, but the neural networks initially predict something, it is wrong, it is not correct. Then since you know what is the expected output, you compare with the expected output. And then after comparing with the expected output, so while coming back, the neural networks tries to correct itself and makes the prediction better and better and better. And there are a lot of mathematics, complex mathematics that is taking place in between. So where you have the forward propagation and backward propagation and the loss function and the optimized function, etc. So which while doing the hands-on, I will tell a bit about that. But right now, I don't want to go much into that, but we'll just try to understand from the next slide, we'll try to understand what is the difference between traditional programming and machine learning. Okay. So I think almost all the participants, including the students, you have some exposure to traditional programming. So in traditional programming, what we try to do is that you try to input the data and some rules and you get the answers. For example, you give the data X and you give a rule that Y is equal to 5X plus 1. Okay, so this is a rule or something, or you have a large marks of the students in the state and you want to do some calculation, you want to find the highest or the maximum 10%. So in that case, you have to do some calculation that is called as a rule. And that particular calculation that you do, that you use some programming language and you use sometimes it may be you write a function like y is equal to 5x plus 1, or sometimes you write an if else, if like this, else, if else, or some decision statements, and then you try to get your answer. So you have the data, maybe the data is being given as a local variable or a global variable or in files or in database, and then you have the programs that are written, and some of these rules, some of the codes are written, and then you get the answers. So this is what you normally follow in the traditional programming. But machine learning is totally different. So in machine learning, so this is the traditional programming, you give rules and data are being input and you get the answers, as I just mentioned earlier. So in the previous case, as you know, so if you give 2, what will be the output that you get? So if you are giving 2, you will get 5 into 2, 10 plus 1, 11. Your output will be 11. So you are following some calculation based on this rule. If you are giving 2, you get 11. If you are giving 1, you will get 5 into 1, 5 plus 1, 6. You get 6 as the output. Okay, but here in the machine learning, it was not like that. So here we are trying to model the human brain, the way human beings learn. As I said earlier, for human beings to learn, for a child to learn, for us all to learn, we see so many things. We know what it is. So we see the data and we see the answers. We get the answers. We infer from the mind through experience by seeing so many things. You see an apple, then you see a mango, you see different types of mango, you see different other banana, and you know that in your mind you understand the shape is this way, the color is this way, and then you know. So in the similar way, you try to give the data, and just like you fed in X-rays in the documentary that you saw, you give so many data and the expected answers. Okay, so you're not giving the rules here, you give the expected answers. So like you say, if it was X in the previous case, it was X and 5X plus 1. So you're not giving the rules here. You just simply say, data is X, and you give here. So here, if you're giving 1, you give 6 here. You give 2, and then you give 11 here. Okay, so these are, for 1, your expected answer is 6. For 2, your expected answer is 11, because actually, and then the machine will try to figure out what is the relationship between this input and the output. What is the relationship between the data and the answer? Or the neural network will try to figure out what is the relationship, and then it will give out a rule, give out the rules, rather than we ourselves giving the rule. So that is what we are trying to do, the basic principle in machine learning. So you can look at this particular example. So I have given 2 sets of numbers here, X and Y. You can pause for a moment and think, is there a connection between these 2 numbers, X and Y? Is there a relationship between these 2 numbers? Yeah, I think you would have figured out. So when you are trying to figure out whether there is a relationship between these 2 numbers, you are trying to think, okay, here it is -1, here it is -3, here it is 1, it is 1, here it is 2, here it is 3. Is there some relationship between X and Y? So you're looking at the input, you're looking at the output. You're looking at the input, you're looking at the expected answers. So, and then you're trying to figure out, is there any relationship? Is there any relationship? Did you find out any relationship? So the process of finding this relationship in your mind is called as machine learning. You are trying to do that with your brain. And if you have carefully observed, you would find that this is 2x minus 1. Yes, there is a relationship. Y is 2x minus 1. So you have 2 into 3, 6, minus 1 is 5. So all these are 2x minus 1. So 2 into 1, 2, minus 1, 1. So everywhere, so 4, 2 into 4, 8, 8 minus 1, 7. So these 2 sets of numbers have a relationship, and that is 2x minus 1. So how can we model this using a machine learning model? So if it was a traditional programming, what would you do? In traditional programming, you would write a program like this. So you would say, okay, float y is equal to 2x minus 1, and because you know this rule, so you know the rule, and then you are trying to return y. You are trying to get the output. You are trying to tell what is the answer using this rule. This is what you were trying to do in the machine learning approach. You didn't have these answers. Okay, so you just had the x values, and then you knew the rule, and then you wrote like this. But in machine learning, you are trying to understand the relationship between these 2 sets of data. And for that, there are so many mathematical methods where you can try to do some regression. So where you can try to draw a linear model, and you're trying to separate this data, and you're trying to fit a line across this data and see, okay, so if you're able to fit a line across this data, then you can predict for the next number what it will be. Okay, so you will learn more about some of these machine learning techniques and some of the regression and classification methods in the subsequent sessions. But just for you to get a taste of what is happening, the mathematics, what is happening inside, I've just showed the slide. So this is an example for a linear regression where you can separate data using a line. And here, this is an example for a logistic regression, so which can classify, will it rain? You give a lot of data about the statistics of rain in the past so many months or so many years, and then you can predict, oh, will it rain tomorrow? Will it rain or not tomorrow? So you can use a logistic regression for that. So there are, for classification, there are so many other methods. There are supervised learning and unsupervised learning. And so whatever we were discussing so far have been supervised learning. So where you give an image, give an input, and then you were trying to give the label also. So this X-ray you gave, and you gave what is the expected output. Okay, so that is called as supervised learning. Okay, so with that basic understanding, let us dive into a hands-on session where we'll try to do something hands-on. And I said we'll be talking about TensorFlow, and you will be doing some hands-on on TensorFlow and Keras. So before working on your hands-on, I'll share the link, and you can also work on your own. But before that, I'll just try to explain what we'll be doing, and then you can do on your own. Okay, so I just, in the previous slides, I was mentioning about two sets of data. So X's and Y's. And so now, instead of using the traditional approach of writing a rule, so we are trying to use machine learning and deep learning techniques here. And we are trying to infer, we are trying to predict what is the, okay, you have a set of numbers. So you have given -1, 0, 1, 2, 3, 4. Okay, these are the known numbers that are given. And you know the answers. Why? Okay, this is for -1, it is -3. For 0, it is -1. For 1, it is 1. For 2, it is 3. For 3, it is 5. For 4, it is 7. So now if you're asked, okay, what will be the output for 10? What will be the output for 15? What will be the output for 15? Some data which are not given in here in the input set. So will we be able to predict? Okay. So not in the traditional way. So now we will use a neural network to predict this. So this is a very simple regression problem for which you don't need a deep neural network. But just to understand the concept of deep learning, I'm just giving you this particular example. Okay. So in order to model the neural network, so this is what we try to do. Keras is an API or application programming interface, which lies on top of TensorFlow. TensorFlow is, as I said, TensorFlow is a deep learning, machine learning library, a tool that is developed by Google. So which is available for free. Anyone can work on it, experiment. There are a lot of built-in data that are available, so using which we can experiment. And so Google has contributed a lot for TensorFlow. And Keras is a general purpose, this application interface, which can work on top of TensorFlow and also some other libraries as well. Okay, so now here there are only very few keywords which you should know before going for the hands-on. So first we need to model the neural network. For modeling the neural network, what you try to do is we say model is equal to Keras dot sequential, Keras dot layers dot dense, unit is equal to 1, input shape is equal to 1. So I know that you have not understood many of these things. So these neural networks, I said you have various layers. Okay, so in order to define these layers in a sequential manner, so this Keras have a function called sequential. So where you can, in this case, we are only using one single layer. So we only have a single layer, and dense is we can, so using sequential, you can, maybe in the next exercise, you will see that you can have additional layers. So here, by this dense is a function again from Keras, where you can design how many neurons you need to want. So what is the nature of the input? How many inputs you have? So here, for this simple neural network, you are just going to use one neuron. So that's why units is equal to 1. And you say input shape is equal to 1. So in this particular case, your input is X. So you are just giving one input and you are trying to predict the output. Okay. So it is just a single layer. This is a very basic, like in programming, you say the hello world program, where you try to print a hello world. So this is the hello world simple neural network, where you have a single layer, a single neuron, and a single input. Okay. So after defining this particular model, now, as I said, you have to through this neural network, you have to pass the input. You have to pass the input, and the neural network tries to learn this particular input, and then so it will predict something random. Maybe whatever it predicts might be wrong in the initial instance, and then you know what is the actual answer. So okay, so you are giving -1. You know the actual answer is -3, but while training, you know, it might be predicting something really wrong. Okay, so when it is predicting something wrong, we need to have something called a loss function. So this loss function will calculate what is the error from the expected value. So the loss function, so here there are different types of loss functions that you can use. Here in this particular case, because this is a regression, you are using a mean squared error as the loss function. So there are other loss functions also which you can use, you know, which I'll not be discussing here now. So cosine similarity, KL divergence, etc. There are different loss functions, but so using this loss function, you are trying to understand what is the difference between what is the error. Okay, so after finding the error, going through the forward of the neural network, okay, predict something, and then you find the error, and while going back, so while going back the neural network, that is called as back propagation. So you will try to adjust the neural network. So there are weights and biases, etc., which will be adjusted, and then you make a new guess. Okay, so initially you made a guess that was wrong; it was far from the expected answer. But now afterwards you make a new guess, and for making the new guess, you use this optimizer. You use something called optimizer. So in this particular case, we are using a very simple optimizer called a stochastic gradient descent. And that is what we normally use for some simple data, you know, for like some regression. So for some complex data like images and all that, so you will be using something else. So you know there are optimizers with you know, like Adam optimizer and RMS prop, etc. There are various other optimizers which also you will be using in the next exercise. But here, just understand that you have two key words here which I mentioned. One is loss, one is optimizer. So loss is calculating the error between the expected output and what is predicted by the neural network, and then while coming back during the back propagation, the way the correction is done on the neural network, and then you make a new guess by using the optimizer. And so through this model.compile, you are mentioning, you're specifying what is the optimizer that we should use for making a new guess. What is the loss function that you should use for making this, you know, calculating the error and adjusting those errors, you know, while coming back in the back propagation. So that is what you try to do when you say model.compile. So initially you define your model, then you define the optimizer and the loss function. Then you have to give the input and the output, the data. Okay, so this is the expected input. So XS. So here Python has got some very easy methods, easy techniques where you have numpy array, np.array. So where you can just simply give all the inputs like this. So you can give the inputs -1, 0, 1, 2, 3, 4, and then also you have the outputs here. The expected outputs for -1, it is -3, 0, -1. So that also can be given using a NP array. And then after giving these two, the data, the optimizer and the loss function, and defining, first defining the model, then you have to fit the model. So fitting the model is this process of going back and forth and trying to adjust. So many times, you know, you try to adjust. So if it is here, these are two sets of data. Maybe you're trying to fit a line between these data. You're trying to identify a relationship between these two data. So it is actually 2x minus 1. You're trying to draw a line between them. You're trying to fit a line here through gradient descent and so many other techniques. You're trying to fit a line. And for fitting this line, you have to go back, go forward, come back, go forward, come back. So now I have said, go forward and come back 500 times. Okay, 500 times. And that's why you say that epochs is equal to 500. So what are you trying to fit you're trying to fit the input xs and ys, xs and ys. You're trying to fit the input and output using this particular optimizer and loss function. On using this neural network, you're trying to fit this particular data. And finally, after fitting it, then you can predict for a new data, for a new value, which is not there. So 10 is not here, okay? So you can predict for 10. So this is what you will be doing for your first hands-on. And you will also understand that when you try to, if you're using a formula, you know that 2x minus 1, 2 into 10 is 20, minus 1 is 19, your answer will be 19. But when you are trying to do it through using a neural network, here the data is very less, and you're only using one layer and one neural network. And because of that, you will not get, your prediction will not be just 19. So it will be something like 18.998, something like that. So it will be something near 19, something very near 19. Okay. So it is trying to say, okay, so what is it? And so through this going back and forth, it is trying to converge on the actual result. Okay, so let's move ahead. Let's go ahead and try to work on the Colab platform. So okay, I'll be just sharing the Google Colab with you now. So I will work on the notebook that is in front of me, and I will also pass on the Google Colab link to you through the chat, and you can look at the Google Colab link. I think we have just received the Google Colab link. So you can, I will work on my own notebook here. So you can also open the Google Colab notebook, and you can work on the Google Colab notebook. So whatever we have discussed so far, you will be discussing on this Google Colab notebook, okay? Okay, so this is, I hope you were able to open the notebook. So this is some of you, this is maybe the first time you're working on a Google Colab notebook or a Jupyter notebook. Don't worry, this is super simple. So you can hear all the, what you're supposed to do is already given here. It is written here. So you can just go through this notebook, and I'll also be running this here. And so you will see various cells here. So these cells, in order to run the cells, you can just hover your mouse, hover your pointer. You can take your pointer, and then you will see a run button on the left side of here. So you can just simply run each of these cells. And when you run the cells, you will be able to just simply run the cells. Okay, so I will run the cells. So just to start with, so this is what we were discussing. So in the traditional method, if you we have to write a program, you will just write float y is equal to 2x minus 1, and you will return y. So this is what you will do on a traditional programming. But here now you are trying to do a hands-on using TensorFlow and Keras. So first, let us import TensorFlow. So we are going to import TensorFlow. So the advantage of working on a Google Colab is that, so whichever system you're working on, you don't have to install TensorFlow on your system. You don't have to install Keras on your system. So you're directly working from the cloud, and TensorFlow has already provided all these provisions for you. And so I'll be just simply running these cells. You can also simply run these cells and go through the text cells that are given below. You can run the cells by taking your pointer to this run button on the left, or you can just simply click Shift Enter or Control Enter. So you can just click on the cell and then you can press Shift Enter or Control Enter. So that is also a way for running each of these cells. So let us initially run the first cell. So we are importing TensorFlow as a TF, and you need NumPy to load the data. So you are importing NumPy as NP. And from TensorFlow, so I said Keras is an API on top of TensorFlow. So from TensorFlow, you are importing Keras. Okay, so this is the first cell. So let me run this. So you can say run anyway. So you can run anyway and run the cell, and I hope you're working on a laptop, and it is important that you have a stable internet connection also for you to execute these cells on this notebook. Okay, so I've imported TensorFlow and I've imported NumPy, and we have also imported Keras. And so now let's what is that we are supposed to do now? First, we said what was the first command? We have to model. Okay, so we had for modeling. So model is equal to tf.keras.sequential. Okay, and then we have only, I said one layer, just one layer. That's why you have only just one line, one layer, and you have only one neural network. That's why this units is equal to 1. Dense is the function given by Keras to define the neural networks. Okay, so here you have one unit, single neural network, and you also have just single input. So you can run it either through Control Enter or Shift Enter, or by running this, clicking on this run button. Okay, so now we have created the neural network. So after creating the neural network, I said the next step was we have to compile it by telling what is the loss function that we are going to use, what is the optimizer that we are going to use. Okay, so in this particular case, so you can also read through the cells here. That will give you a clear explanation of what we are doing. So the neural network is trying to learn. Okay, so initially, as I said, it will be learning wrong. It will be making a wrong prediction, but using the loss function, it will assess the error, then come back. And now, as I said, we were defining, we are wanting to go 500 times back and forth. So it will keep guessing, keep guessing, keep guessing, keep learning. And finally, we want it to predict correctly. Okay, so the next cell here, as I said, model.compile, the optimizer that we use is stochastic gradient descent, and the loss function is mean squared error. Okay, so let me run the cell. So now we have defined the optimizer and the loss function. Now we need to provide the data. Okay, so we need to provide the X and the Y. So we are not giving the rule now, we are not giving the equation, we are not giving the formula, we are just giving the input and the expected answers. Okay, so we can just simply using np.array, we can feed in the data, and I'm running that cell as well. I hope you are also able to do it on your own notebook. Okay, so now let me train the neural network. Okay, so I will clear this output, and then let me train this. So for training, I said model.fit. So model.fit. So you are giving the input X, input Y, okay, and then you are trying to fit these data. Okay, what is the best way? What is the relationship between these data? And in order to do that, we have already defined the optimizer and the loss function, and we say, okay, let us go back and forth 500 times, 500 epochs. Okay, so let me run this. So it will keep displaying the 500 epoch 1, epoch 12. So it's, my system is very fast here. I have a 100 Mbps connection. That's data is very, very small data for you also. I think it will take place very fast. And you will, if you observe, when you are trying to fit the data, so the loss should keep decreasing. Okay, so the loss, so initially the first prediction, the loss is, so you look at here, so the predictions. So I've completed 500. So initially the loss was 0.0336, and the loss now it is decreasing and decreasing after you go back and forth. So here it is decreasing, 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 and decreasing. And so when your loss is decreasing, keeping on decreasing, that means your accuracy, as you keep going back and forth. So 500 times, 500 epochs have been completed. You went back and forth. And so now your loss is very less. So this is exponent to the power minus 0.05. And so your loss is very less now. So let's predict and see. So now you have built a neural network. You have defined the optimizer. You have defined the loss function. You have compiled it. And now something great. You are going to predict. Okay, so you're not going to write a traditional program, but you are using a neural network to predict. So let's see what is the prediction that you will get. Okay, print model.predict 10. Okay, so you are giving 10. So this 10, as you observe, 10 is not there in the input data. So the neural network is only trained with -1, 0, 1, 2, 3, and 4. But now you are giving a data which the neural network has not seen. Okay, and you want to predict. And let's see what it will predict. Yes, as we said earlier, now it is predicted very fast. It is predicted that it is 18.97676,715. Okay, so what it should have been 19. So the actual result should have been 19. But now, because the training has taken place with just 6 data, very, very less data. Isn't it 6, 1, 2, 3, 4, 5, 6? Yes, just 6 input data. And you just gave 6 input data, 6 labels, and it's very insufficient data. So that is why your accuracy, though it is quite accurate, if you're rounding it off, it will come to 19, but still this is not exact. And you can find the model summary here. So this is a model that you have used. You have a dense layer, and these are the parameters are 2 because of this bias also. So you don't have to bother about it right now. So I hope you understood these steps of the simple, how you can create a neural network and how you were able to work on it, how you are able to compile it, how you are able to fit, and how you are able to predict. So I hope you are able to remember these words. So what are you trying to do? First you model, then you compile, define the loss function and the optimizer function, and then you fit the data, and after you fit the data, you can predict. Okay, these are the basic workflow in deep learning. Okay, so now let's go back to our slides. So I hope it was clear till now. In case you have some questions, you can post it on the chat box. We'll take it up in the end. Okay, so now we saw a very simple hello world example for deep learning, machine learning. And so let's move ahead. Okay, so let's see, we are trying to do a traditional programming for an activity recognition. Now, imagine that you have got some pictures like this of a person walking, running, then cycling, and then you see some other picture here. The person is golfing actually, but you see some of these pictures and you have some data. Okay, so you know that the data is for walking, the speed is less than 4. And if you want to write a program, this is how you will do. You will write a program by saying that if speed is less than 4, status is walking. Okay, this is the way you approach traditionally in traditional programming. Okay, now, so you have the data that, if the person is, if it is like this way, if the speed is beyond that 4 and above, it's running. Okay, so if this is your understanding, then you will write the program. So that is your rule. You write the program in this way. If speed is less than 4, status is walking. Else status is running. See, all of you have got some exposure to programming. So you know that this is how you write. And then, okay, so you want to extend that further. And now you have some data that for a person who is cycling. Okay, so for the person who's cycling, you realize that, okay, the speed of cycling will be faster. And then you write a program by saying that if speed is less than 4, status is walking. Else, if speed is less than 12, okay, status is running. So you're saying that from 4 to 11, so less than 12, okay? So 4 to less than 12, you say say that it is running. Then you can write the program like this. Else, if speed is less than 12, status is running. Else, you say that it is biking. Okay, so you're writing the code like this, and you find it difficult. See, how can, in fact, writing like this itself is, it's not realistic, because how can you say the speed of running or walking? So there are different scenarios. The person may be climbing a hill. If he's climbing a hill, the walking speed might be much lesser. The person may be running down a hill. So if the person is running down a hill, then the speed might be much faster. So you cannot actually program this way. Or, okay, let's imagine that you are successfully able to program thus far, and then you are given a scenario like this, an image like this, then how will you program this? This is neither walking, neither running, neither cycling. A person is standing like this, and then from your human mind, because you know this picture, you have seen it, you know that this is golfing, the person is playing golf, but how can a program be written this way? So you come to the end of yourself, you come to the end of traditional programming, you see the limitation of traditional programming, and that is why you need machine learning or deep learning. And that is why, instead of this, you go for a different approach. So you say you feed the neural network with thousands of images of a person walking, and then you label it, okay? So the image contains a lot of data, and you're just feeding the neural network with those data and a label saying that this is walking. So this is another image of a person with a lot of data, and then you label it running. And then there is another image here, and then you label it biking, and here you label it golfing, and then you have lot of separate images of people walking in uphill, downhill, or whichever way the person walking, different types of images, and you pass on, feed this on to the neural network, and the neural network, as I said earlier, as we did earlier, hands-on, tries to figure out what is happening. Okay, what is inside this? And it tries to learn, just like a human being tries to learn. And then the neural network is able to recognize even some image when it is given, which it was not seen earlier. And that is where the neural network, the deep learning has taken off. And that is why our autonomous driving and all these things have become a reality. So let's take this computer vision example. So you can look at these pictures. You can look at these pictures, and I'm sure you will tell what these pictures are. You will say this is a coat, this is a shirt, this is a pants, this is a shoes, and this is a t-shirt, frock, a handbag, etc. So how did you know that? You know it because you have seen it earlier. Your mind you have seen a lot of such images and you can recognize it. But if it was an alien, someone extraterrestrial coming here, and then we are showing this image and asking the person to tell what this is, the person cannot tell because the person has not seen. Okay, so the neural network needs to be trained in order to infer. Neural network needs to be trained in order to predict. Okay, and so before going ahead and doing the next hands-on session, I will just mention some of the computer vision tasks. So these are some of the terms that you commonly come across in the literature. Image classification. So what is image classification? So image classification is, so you see this particular image. In this particular image, you have a chair. So the result of the image classification is, if you feed in this particular image, the output says that it's a chair. Okay, so you get this because you feed so many chairs and images of chairs to the neural network, and the neural network learns, and the neural network then finally classifies. When you're giving a chair, it says, okay, this is a chair. Okay, so now you your classification is not enough. You also want to locate where the chair is, or you want to draw a bounding box across this image and you want to locate, okay, this particular image. So that is called as image classification plus localization. Actually, object detection is that. Object detection is an extension of image classification plus localization. Okay, so here you are not just in image classification plus localization. Here you are not just telling that it's a chair. You are also telling the location of this chair. So you can just mention, you can just identify what is the left corner coordinates of this left corner, coordinate of this right corner. So if you get the left coordinate and this right corner coordinate, you know the bounding box, okay, this rectangle here, and then you know that it is located here in this location in this picture. So there might be multiple images, multiple objects in your image. Okay, so here you have a chair, you have a dustbin here. Okay, so by object detection, you are not just classifying this alone. So you are classifying and you are localizing multiple objects. Okay, so you are saying, okay, this is a chair. Okay, so you will label it, and you will also mention the left corner, right corner coordinates. You will also say, okay, this is, I'm sorry. So this is a dustbin. And for this dustbin also, it is located here. This is the left corner and this is the right corner. So this is called as object detection. And then another word that you come across is segmentation. What is segmentation? So in segmentation, you are not just doing the object detection. So you want the exact boundary of the images of the objects in your image. And you want the exact boundary, and you want all the pixels within that boundary. Okay, so you want all the pixels within this particular boundary. So you know, okay, this is a chair. This segment has been, this chair has been segmented out. This dustbin has been segmented out. And there are you can pass on various images and use various techniques to do these tasks using deep learning. Okay. So now we'll move on to the hands-on to classify images, and for classifying the images, we'll be using the FashionMNIST data. Okay, FashionMNIST dataset. The FashionMNIST dataset is a dataset. As I said, now deep learning has become very popular because you can do a lot of experimentation. There are a lot of datasets available, even with TensorFlow. These are all loaded within. You can just load it from TensorFlow. These are all part of TensorFlow that is made available. And so this FashionMNIST data, this is a set of 70,000 images. Okay, 70K images, 70,000 images are here. And these 70,000 images, and these are of 10 categories. 10 categories. So I said, in order to train the neural network, so we are going to train a neural network to do some computer vision or image classification task. And for that, so here you look at the classes. So you have a t-shirt, you have trouser, you have pullover, then dress, coat, sandal, shirt, sneaker, bag, ankle boot. These are the 10, 0 to 9, 10 categories. And each of these categories are labeled using numerical numbers. So if you are just simply using these English words, t-shirt, trouser, pullover, etc., then there will be a limitation, because so only English speaking people can understand. Okay, so we want to reduce the bias of any bias for any particular set of group of people or anyone. So that's why you normally label these particular classes that you have. Okay, so now t-shirt is 0, trouser is 1, pullover is 2, dress is 3, coat is 4, sandal is 5, shirt is 6, sneaker is 7, bag is 8, and ankle boot is 9. So these are very tiny images, and so because of that, it will not take much of computing power, and so that has been very efficient. But you have the minute details using which the neural network will be able to classify what is a shirt, what is a handbag. There's a handbag here. What is a handbag and what is a shoes? So it can. So these images are of size 28 by 28, and hence we can train a neural network using this particular data. Okay, so we are going to. As I just mentioned, these are the description of the classes and the labels. And so let me, before going to the hands-on session in the notebook, let me just mention what we are going to do as we did earlier. So we'll be importing the TensorFlow. So import TensorFlow as TF. And from TensorFlow, we'll import Keras. Okay, so now we can just simply FashionMNIST. So we can simply define FashionMNIST. FashionMNIST is equal to keras.datasets.fashionMNIST, and this is part of since this is part of this TensorFlow Keras platform, we can just simply load these images. Okay, so we can just simply say FashionMNIST.load data. Okay, so we have said FashionMNIST is equal to keras.datasets.fashionMNIST. So we are taking the FashionMNIST from the Keras datasets, and we are assigning this particular name, FashionMNIST. Okay, FashionMNIST, and this FashionMNIST can be loaded here. FashionMNIST dot load data. So using this load data function, you can load it. Okay, so while loading it, again here there are two terms. There are 4 terms which I think we have not talked about it so far. One is train images, train labels, test images, and test labels. Okay, so as I mentioned earlier, so we have 70,000 images. So out of this 70,000 images, so when we are going to train, what we are trying to do is that we'll be using 60,000 images for training. Okay, so we're training our neural network using 60,000 images, and then 10,000 images will be used for testing. Okay, so we'll have so train images. So this this fashion MNIST data is classified in that way here. So you'll have 10,000 images, 60,000 images for training, and so you will have 60,000 training images, and then you will have 60,000 labels. Okay, what do you mean by label? Images, it could be a shoes, and then the label is okay. This is an angle boot, so the label is 9. Okay, so you're using this numeric value in order to, as I said earlier, in order to avoid the language bias. So since it is 9, can be understood by the people who understand Japanese or Chinese or whichever language, they can understand 9. So we'll be using these training labels. So you will have 60,000 training images, and then you will have 60,000 training labels. So these 60,000 training images are of 10 classes. Okay, so these 10 classes, you will have 6,000 images of the angle boot, of coat, of shirt, etc., and you will be training. And then you will also have 10,000 images, so 10,000 test images and 10,000 test labels. Okay, this is for your testing after training. So these test images will not be part of the training. So you will do the training, the neural network will learn only from the training images, and then afterwards you will be testing from these images with which we have not trained the neural network. So we'll try to study, we'll try to understand the accuracy of our neural network. Okay, so this is the basic first step that we do to load the fashion data. Okay. And then we have to model. Okay, so by modeling, we said we have to define the layers. Earlier, I said we only had one single layer, and we only had one single neuron, and we only had one single input data. But in this particular case, so what we are trying to do is that so our model is equal to Keras.sequential. And here we have 3 layers, okay, 3 sequential layers, and then this sequential layer. So I said we have our data was, each of this image was of shape 28 by 28, 28 pixels by 28 pixels. Okay, that was the input shape. Okay, and in order for these neural networks to process it much easier, so we'll be actually flattening. So this 28 by 28 will be like a matrix, and so we'll just flatten it. By flattening it, what we are trying to do is that we'll try to make it a vector. So 28 into 28 is 784, right? 28 into 28 is 784. So we'll make it a vector of size 784 by 1 through this flatten function. Okay, so we are feeding in these images, okay, of as a vector of size 784 by 1 using in this first layer. And then after that, we have the dense layer. So in the dense layer, earlier you had only one neuron, but here, so we are using 128 neurons. So since these are images and we want more neurons to understand this particular image, so though we are using only a single hidden layer here in between, but we are using 128 neurons here. And using these 128, after this 128 neurons, so you are also defining an activation function. Okay, this is another word which you have not seen earlier. So in the subsequent classes, you will be studying what an activation function is. But for the time being, you just need to understand that an activation function is something that you use in order to bring in non-linearity to the input data. And so here you will be using an activation function called ReLU. ReLU stands for rectified linear unit. So this ReLU, what it does is, it will actually suppress all the values which are less than 0 to 0, and all the values which are higher than 0 will be retained as it is. So that is what you use during using a function called ReLU. Okay, so there are various activation functions, and ReLU is a very good activation functions which we normally use. And so talking about the various activation functions is not beyond the scope of this introductory class. So you will you listen to more discussions on the activation functions in the subsequent class. So you just need to understand that you have given the input as a flattened input, and then you have 128 layers. You have a layer of 128 neurons, and the input is passed on to that. And then there are various other components like weights and biases which are passed on, and then this activation function does some introduces some non-linearity into that, and then finally you need to predict. Okay, so from these data images that you have given and some processing that you do inside this neural network, afterwards you need to say, okay, what is the output? So you are giving an image, okay, it could be a shirt, and you need to predict that it is a shirt. And for predicting that it is a shirt, so here this is a classification, and you have 10 classes. As I said earlier, you have coat, you have shoes, you have bag, you have so many things. You have 10 classes. So using an activation function like softmax, the softmax is used to classify in the final layer. So you will classify whatever after processing everything through the neural network. When you get at the output, oh, either it is a shirt or it is a bag or it's a shoes. Okay, so that is why you will classify between the 0 to 9, and that is why you have 10 dense layers here in the final layer. Okay, so even if I'm sure, I know that you have not understood fully what is an activation function or what is ReLU or softmax, but just understand that now you are giving the input, you are doing some processing here in between, so you are defining 128 neurons here, and finally you need to get 10 classes, and that's why you have this 10 here. And for moving ahead from one state, one layer to the next layer, there are some calculations taking place, and those calculations are defined by the weights and the activation functions and all these things. And a bit of it you will study in the subsequent sessions. Okay, so basically you understand this is how you define the model. So here you are using the flatten, then you have 128 neurons, then you have 10 dense layers finally in order to classify 10 of these various images. Okay, so now with this introduction, let's go to the notebook, Google Colab notebook. Okay, so I hope you were able to see the notebook here. I know that some of you who are new, you may be having some difficulty in understanding, but if you are working on this notebook, so our next session is only on the next Saturday. So next Saturday, from 3 p.m. to 5 p.m. we will be having the next session. So before joining the next session, so I have already shared 2 notebooks. Now earlier we have worked on 1 notebook. Now this is the second notebook, okay, which I am sharing. And whatever I have talked so far, it is given in this particular notebook. So if you patiently read through the notebook and execute the cells that are here in the notebook, you will thoroughly understand what we have discussed so far. Okay. And so through this workshop, since we are covering quite a few portions, introductory material in this initial workshop, so that's why I'm going a bit fast. And also the crowd who are attending this workshop, there are some people who are very new, some people who have some exposure, and so we need to have a balance between these two groups. And so that is why you are given these notebooks so that you can keep working on it as homework. And in this particular notebook especially, you will have a lot of exercises also towards the end, and thus you will be able to do those exercises on your own and understand it very well. I know that this is a long session also, and because this is a long session, I think some of you students, if you want to take a break, you can. There is no problem. You can take a break. I have shared the notebook. You can go through the notebook later on as well. Okay. But anyway, let's, for others, let's just continue. So this is the beyond hello world. So this is a computer vision example. So we are trying to, where we are trying to classify the images. Okay, in the similar way, we'll import TensorFlow, run anyway. So I'm importing TensorFlow as TF, and I'm also trying to print the TensorFlow version. So those of you who are curious to know which version of TensorFlow we are working with, so we are working with the 2.3.0 TensorFlow, which is the latest version. Sometimes if you're working on your own system, you may not get the latest version, but since you're working on a Google Collaboratory, so this 2.3 version has already been integrated with the Google Collaboratory, and that's why you're able to work with the 2.3 version. So even after, hello? Okay, so then so we say that we want to get the data, we want to get the fashion MNIST data of those 10 classes. So I said there are 70,000 images. So we want to get those data, and now I'm going to put it here in this MNIST. Okay, MNIST is equal to tf.keras.datasets.fashion MNIST. That's already part of the Keras dataset, and so we can just run the cell and get the data. Okay, so we have got this data, and as we did earlier, the training images. So we can just simply load the data, MNIST. So we have already stored the data or in MNIST. Okay, so the data is there in this particular variable MNIST. So we can load the data from using the function load data. So MNIST.load data, and we want the training images and the training labels as well as test images and test labels. So we have 60,000 training images, 60,000 training labels, 10,000 test images, and 10,000 test labels. So let's run it. So the data has been downloaded. Okay, so now we have downloaded the data. Let's see what is the shape of some of these images in this data. So if we want to look at the shape of some of the data, we can run the next cell here. So we are importing NumPy as NP, and we want to just have a boundary. Within a particular boundary, we want to have a line width of 200, and within that, we want to plot this particular image as the pixel values in this particular image. Okay, so that is what we are trying to do using this particular cell. And so here we are just plot.imshow. So this is a command in Python where we can display the image, the training image located at location 0, okay, and the training label at 0. The training image will just print, okay, the shape of the image at 0, then the label at 0, and what is the training image at 0. So we'll just run it and see what you get. So when you're running it, so you're getting an image like this. So at location 0, so here you see that there are these are the pixel values in this particular image. a lot of zeros here, some high intensity values here. Okay, so these pixel values are between 0 to 255, and you see a lot of values here. And when you see the image, you know that this particular image is a shoes. Okay, so this is a shoes here. And now if you were looking at the labels earlier, you know that at 0, this is shoes. Okay, so this is just, we were trying to understand what is in this data. Okay, if you want to look at something else, okay, you can just simply change this. So let's see what is there in 100, location 100. Okay, so I changed plot imshow, training image is 100, training label is 100. What is at 100? And I want to print it. Now it is something different. Oh, this is this is a handbag. This is a handbag. So we have images. So this data set has got various types of images, and computer can, even if it is an image, computer can only understand numbers. And so that is why you have all these pixel values displayed here. Okay, so what is that? So here they have said, let's look at what is at 42, at index 42. At index 42, what is at index 42? Okay, so this is again a boot shoes here at this index, a different type at this index 42. So you have so many images at these indices, and you are training the neural network with these images, and you are giving the appropriate labels, and then finally our neural network will be able to predict the right class. And so we normally do a normalization. So before sending it here, before the neural networks process it. So this neural network, this normalizing. So here I said the pixel values are between 0 to 255. So we want to make it between the range 0 to 1 in order to make the processing easier, and the neural network in order to make it easier. So we'll normalize it. And so that's why you are dividing the training images by 255, and the test images also by 255. So this is just for normalizing the images. So you run the cell and you normalize it. And after normalizing, so what we are supposed to do, as we discussed earlier, so we have to define the model. So we have to define the model. So we have to define the sequential layers. So first, we discussed earlier, we have a flattened, we'll be flattening the input. The 28 by 28, we are going to transform it to 7841 using this flatten function. And after flattening it, you have a dense layer of 128 neurons. And this is a second layer. And then you have the final layer where you have 10 classifications using a softmax activation function. You need 10 classifications. That's why you have these 10 layers. And earlier, so you used a ReLU activation function. Okay, so these are how you define the model. Okay, we just discussed it, so let's just run it. So we have defined the model, we have created the neural network now, and all the details. So what I've just mentioned is given in this notebook. For the lack of time, I don't want to go further into it right now. So you can just go through this notebook, try to run it again. There are some exercises at the end where you can experiment with different values. For example, here I have given 128 neurons. So what will happen if it is 512? So what will happen if it is 1024? If you increase the number of neurons, what will happen? What will happen if you include one more layer? Okay, so these things can be experimented. There are some exercises at the end for using which you can experiment those things as well. You can as well try out different activation functions as well. But at the end, you need the softmax because you need 10 classifiers. Okay, 10 classifications. So the next thing that we need to do is compiling and fitting. As we have been discussing, this is a consistent pattern. First, we define the model, then we compile the model. While we are compiling the model, we have to define the optimizer function, we have to define the loss function, and then we fit the model. And this is the way that we do. Okay, so here now we are compiling, and so while compiling, so we are using the optimizer function. So here with the optimizer function, we are using as an adaptive optimizer called ADAM optimizer. So I don't want to discuss more on this particular ADAM optimizer right now, but know that we are trying to bring a nonlinearity, and we are trying to push the data from one layer to the other in order to help this process of learning through the neural network. And for understanding the loss, okay, so I said you will predict something wrong earlier first, and then you will correct the errors. And earlier you used the mean squared error loss function, but here now you're using a categorical cross entropy function, so which is a loss function that we are using. So this is normally for classification we use a function like this, cross entropy, but for regression we can use mean squared error. So earlier it was when we were predicting from a set of numbers, we were trying to do regression, and so we could use mean squared error. But for a classification, we normally use cross entropy loss function, and we want to also display the accuracy while the training is going on. So that's why we are using a matrix, which is also built in as part of TensorFlow. Okay, so the optimizer loss function, and now in order to display the accuracy, we are using this accuracy term. And then after defining the loss function and the optimizer, now we can fit the data. So okay, we can fit the data. So while fitting the data, so we have the training images, we have the training labels. Okay, so we are trying to tell the neural network to learn. So what are we inputting? We are inputting just like we inputted the X and Y earlier. So here we are inputting the training images. So this is the input. Okay, training label. What is the training label? This is the expected output. Okay, so you are giving the expected input. No, you are giving the input and you are giving the expected output. Okay, so training images, training labels, and you are saying epochs is equal to 5. So that means you say go back and forth 5 times. Okay, go back and forth 5 times so that the neural network can learn. So since these are the number of images are more, so it will take more training time, and that's why I've made the epochs is equal to 5. So let's run this cell. So we are compiling and we are fitting. So you can also run it on your own machine, and you will see that it is taking more time than that we did for the numbers. But here also you see that you look at the loss function, the loss will keep decreasing and the accuracy will keep increasing. As the network trains, the initial guess will be wrong, and then it will, using this optimizer function, it will make a new guess. and it will calculate the error using loss function. And you see that here initially the accuracy was only 82.6%. The initial accuracy was 82.6, but finally you see that the accuracy has increased to 89.14. So you're able to, you have built a classification within just this introductory class. Now you have built a classification model, and you have fit the data, you have defined the optimizer function, you have defined the loss function, you have fit the training data and the training labels. And now let's evaluate what we have done. Okay, so all these data have been trained so far, but now let's evaluate it with the test data. Okay, so we can, in order to evaluate with the test data, we can say model.evaluate with test images and test labels. Okay, so this, we are trying to evaluate it and see what is the accuracy. And then finally, you can predict with an unknown image using model.predict. So now we are trying to evaluate with the test images. So we said that there are 10,000 test images and 10,000 test labels. So we can evaluate model.evaluate using the test images and the test labels. And you find that though the neural network has not seen any of these test images, while evaluating, you have got 87% accuracy. 87% accuracy. Earlier, you had got 89% accuracy with the training data, and it is now obvious that the accuracy has decreased a bit because the network is now training and testing with unknown data, the data which it has not seen earlier, it has not been trained with earlier. Okay, so this is the accuracy now that I've got 0.8761. Not 8831, 0.8761. I've got this accuracy. You might get a different accuracy, and you can try it again, try it out. There are a few exploration exercises, as I just mentioned earlier. So you can try out these exploration exercises on your own. The notebook was already shared with you. And if you do this exploration exercises on your own, you will understand it very well. You can change the number of layers. You can change the number of neurons. And all these things you can change and you can modify, and then you will see how the neural network, the performance of the neural network varies according to these changes. Now, since we said our time is till 5 o'clock, so let me go back to the slide, and we'll try to discuss the remaining part. I hope now you're able to see the slides. Okay, so we have been working, and so before we conclude, let's see one more video.
I am AI. Accelerating your discoveries to solve the great challenges of our time. Visionary, bringing characters to life with more natural movement, generating brilliant new worlds for them to explore, and inventing new ways to bring out the creative genius in us all. I am a protector, leading the way into the most dangerous environments and searching for signs of life. I am a guardian, listening for the sounds of destruction to save our forests and using satellites to bring freedom to those who are enslaved. Finding safer paths for cross-country deliveries and taking personal travel to new heights. I am a scientist, exploring ocean oceans of data to understand extreme weather patterns, and studying the building blocks of life to save a community from hunger. I am a healer, giving hope to those who suffer from the most challenging diseases. And tapping into the brain to rejuvenate paralyzed limbs. I am even the composer of the music you're hearing. Brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Okay, so this was just a platform, this was just an introduction. So you will be learning more of this in the subsequent sessions, and you can explore a lot on your own. There are so many platforms that are available for you to learn machine learning and deep learning. I myself took these opportunities to learn from some of these platforms. Some of you know that I was into some administrative responsibilities earlier for many years, but during that time I wanted to move to an academic research field, and I learned something on my own through Coursera, Udacity, Udemy, and some of these online platforms. So there are many such online courses available on these platforms, and those of you who are interested, I was just trying to give you an introduction and say that there are enormous possibilities and potential for deep learning, and it is not difficult for you to learn. So it is not difficult for you to use it, model it. It is not difficult for you to compile. It is not difficult for you to predict using your own data. So you may be working in different research areas. You have a lot of data, and you want to find meaning for that data. You can use some of these tools. There are so many of the tools. We have just worked with TensorFlow and Keras. There are so many other tools that are available. You have scikit-learn, which is part of the Python, and Piano, Cafe, Spark, PyTorch, Accord, CNTK. There are so many machine learning tools and platforms that are available. But some of these tools are easy. For example, TensorFlow and Keras and the Python, you have a lot of support. The TensorFlow itself, they have their own site and a lot of videos which are helping us to learn. Okay, so that is just an introduction. I shall pass on some of this material also to you. No, you have already passed on your mail. So we will pass on some of these resources, some of these slides, so that those of you who would like to learn further can learn from this. And I know that there are people from different branches here. And for some of you, deep learning can be used for mechanical engineering or chemical engineering. You know that, for example, Shell, they have been collecting real-time data across its operations for decades. So more than 10 million operational variables per minute are presently collected, streamed, archived, and integrated with operational control systems. Okay, so there is enormous potential to exploit these data further. So you can do predictive analytics, and machine learning algorithms could help there. So make it possible. So you can avoid unexpected failures, unnecessary maintenance. Okay, so it could save millions of dollars per year, and not just saving of dollars. So if you can have a real-time camera monitoring some of the sensitive places. For example, we had very tragic gas leaks, chemical leaks, which so many lives were affected. But if there are real-time monitoring and the data is captured, and if there is an artificial intelligence, machine learning, deep learning model that is monitoring, and if it can predict, okay, when something is going to happen, and so we can do predictive maintenance, we can correct it, and life can be saved. Okay, so there are people from management department here. So there are a lot of potential. So for customer service, price forecasting, portfolio management, fraud detection, algorithmic training, trading. There are risk management, credit assessment. So earlier, I think there was a session on by a banking professional. So where he was talking about how he transformed the banking using machine learning and deep learning. So without a single office, so you were able to understand, create customer base and also understand what is the need of the customer rather than pushing some information to the customer and irritating the customer. You can understand what is the need of the customer at a particular time, and then you can suggest that, recommend some product. So all these things are enormous opportunities and potentials for various branches of engineering and management. So finally, let me conclude by just mentioning a few ethical issues. So everyone will be curious about these things. Will robots take over the jobs of human beings? So now you see that robots and deep learning is making a lot of difference. So will robots take over? You can think. Actually, it will not take over. So it is what we need is a reskilling. So we need to learn, reskill, and there will be new jobs will be created. Yes, some of the jobs, repetitive jobs, will become obsolete, but new jobs will be created. With this kind of data capturing and analysis, will we lose our privacy? Yes, it is yes and no. So there are privacy issues. So this is an ethical issue. But there are also organizations are taking care so that they don't intrude into the privacy of people even while capturing data. What are the legal implications when AI systems make a mistake? So that's another thought-provoking question. When can people be blamed if an AI system make a mistake? Can AI systems be used to kill? Can somebody sit and create a robot and train the robot in such a way that if the robot goes out and kills somebody, and who can be blamed? Can the robot be blamed, or the person who programmed the robot, person who created the robot be blamed? What if someone creates rogue AI systems? What about bias in AI systems? Bias in AI systems in the sense, I heard of an AI system that was created, and so for the data set that was used was mainly from one particular region. Okay, so people from one particular European countries, and then when the training took place using the data from an African country or some other country, so it did not perform. So the results were not as expected. So that's a bias. Or sometimes the system, the machine learning system can associate, you say a particular job profile, and you can associate that with a particular gender if the training is not proper. You say a customer service executive, and the system can say it's a lady, but it's not. No, there could be a bias. So it all depends on what data you're training with. And finally, the technological singularity. Will AI surpass human intelligence and then control us? So these are questions that you can think about. So let me thank the Saintgits management team and the college authorities and all the participants. I've used the resources from NVIDIA, TensorFlow, and Deep Learning AI, and for some of their contents. And thank you all. And so if you have any questions, you can, I'll just check the chat box. You can post your questions on the chat box, or you can mail me. So my email ID is displayed here. My email ID is also posted in the chat box. So santhosh.mathew@saintgits.org. So you can mail me and I can reply you. So if you have anything to discuss right now, there are some AI experts also who have joined. So this is not a one-man show. We have a team with us. So the sessions in the coming weeks will be handled by Mr. Nitin Prince John. He's also a well-trained AI expert who has done a lot of projects in AI. We have other experts, Professor Sujuke Swami from our Saintgits College of Engineering is another expert. So he's a mathematics expert as well as an artificial intelligence expert who has been running training programs through additional skills acquisition program of Saintgits ASAP. There are many other experts here in the computer science stream, in the computer applications department. So they will also be able to contribute. So if you have something to discuss now, ask some questions, you can ask now. You can either ask through chat, or you can even unmute and ask. Someone has asked whether this course is only for 3 weeks. So initially, this is for 3 weeks. So I appreciate your interest. So we'll also, for those of you who are attending this workshop for 3 weeks, we'll also provide the resources and a certificate also, sorry. We'll also provide you the certificate. So there is a question here, sir, how is data science connected with AI? So there are so many terms like machine learning, deep learning, and data science is primarily connected with working with the data, trying to understand the data, and especially in the context of a business setup, you are trying to work on the data and make some predictions, stock predictions. So you have a lot of banking related data and you want to understand, and you work on this data. So that is normally an area where we call as data science. But when you talk about machine learning and deep learning, rather than just working with this data and coming out with some results, you are also learning about the algorithms behind it, the process behind it, what is happening. So there are so many people who are working on developing so many algorithms. There are so many people who are working on a lot of research. So normally that particular area is what we call as the machine learning and deep learning area. And data science is more towards the application part of it, especially for this business data. Any other questions? So here we were just using the collab, and we were just able to import TensorFlow, and we were able to work on it. But if you are working with TensorFlow, you can, if you are using a Jupyter notebook, you need to install it. And I think you will be working on some of those things in the coming sessions. And Mr. Nitin Mathew will be, Nitin Prince John will be able to help you in those areas as well. So any other questions? So somebody is asking about reinforced learning. So there are so many areas, so many advanced topics in here where you have reinforced learning and NLP, so many things where, basically for this, in order to answer this question about reinforced learning on a general way, we can say that in reinforced learning, you use a reward signal to tell the AI system when it is doing well or poorly. So just like you tell a child, okay, very good, and then bad, and the child slowly understands what is good and what is bad. In the similar way, you are trying to teach the neural network what is good behavior, what is bad behavior. So that is basically reinforced learning. And a positive reward is given when it does well, and a negative reward when it does poorly. Okay, so it automatically learns to maximize its rewards. And normally this is used in computer games, and so many other areas. Okay, so now it's 5:10, and if you don't have any further questions, if you have questions, so if you have questions, definitely you can please mail it to santhosh.mathew@saintgits.org, or you can also mail it to Mr. Nitin Prince. He actually contacted you with the details of this particular session, so you can also actually mail it to him also. So we'll be able to answer your questions, whatever it may be. And thank you very much for understanding. So if you have any feedback, you can post the feedback here. I hope definitely this session was interesting, and I hope you got a good platform to launch further and learn machine learning and deep learning. And I wish you all a bright career in machine learning and deep learning. Some of you computer students, first year students, you did not maybe fully understand it now, but you can go home, take these notebooks, go through it, run on your own, and definitely that will be a good platform for you. That will help you to definitely definitely take it further and learn, do your own projects, etc. So thank you very much. I don't see any more questions here. Okay, so thank you. I'm glad that some of you enjoyed the session, and all the best to the world of machine learning and deep learning. Thank you, and bye for now. So please be reminded that the next session will be at 3 p.m. on 21st of November. So 3 p.m. to 5 p.m. So use it as a time for learning, and you can also do some projects. Thank you. Bye.